assume we talked about equilibrium.
That was a question.
Pardon?
That was a question.
Have we talked about equilibrium?
I think so.
I think a little bit.
A little bit. All right, what is equilibrium?
Let's stay with equals.
In physics, what is equilibrium here? In motion? What is the requirement for equilibrium?
The two forces acting on each other to be zero?
Equal to each other.
Say it again?
Equal to each other.
They need to cancel each other out.
Yes.
If they're equal to each other, they're in the same direction. Okay. So they're vectors. All right, equilibrium. There are three different conditions. If any one of these is true, the other two are true. One condition for equilibrium is that acceleration is zero. If acceleration is zero, equilibrium. If acceleration is zero, that means my velocity is not changing. So change in velocity is zero. Also, as we will get to in chapter 4, if acceleration is zero, the other thing that's zero is the total force. The total force is zero. So if I have two forces, they have to cancel each other out. If I have three forces acting on an object, well, the sum is zero. So if we look at the person, we have two forces acting on. We have the normal force acting up, and we have the weight acting down. It's supposed to be a B. If he is in equilibrium, so he's standing on the scale, he is not accelerating, not bouncing up and down. Matter of fact, not only is he in equilibrium, he's in static equilibrium, which means he is not moving and not changing that. If he is in equilibrium, then the sum of the forces up equal the sum of the forces down. So YP would equal WP. The scale's measuring this, but if it happens to be equal to the weight, then we say we're measuring weight. But it's indirect. If not in equilibrium, such as bouncing on a scale, then they're not equal, and it is not. You cannot claim it's measuring weight. Unfortunately. There's at least one textbook, the one that we used for 110. Hewitt, the author, he changes his mind partway through the book. In chapter 2, he talks about basically the same definition of weight I do. At some point later on, he says, weight is the force you apply to the scale. No, it's not. There is such a thing known as apparent weight and actual weight. Apparent weight would be the normal force. The actual weight is the gravitational pull.
So was that like a mistake on his part, or did he just decide?
He also calls inertia laziness, which is just, inertia is more stubbornness.
Sure.
Definitely more stubbornness than laziness. Yeah, I mean, the book has a lot of pluses to it, but there are a couple things where he either oversimplifies or I just flat out disagree. Although I did find someone, I found a review of his book, and he hated Hewitt very much. Hated the textbook in extreme amount.
You were looking for that anyway. Like,
Pardon?
I remember you had a great review.
Yeah. Okay. Questions up to here? Then here's the cliffhanger. The next thing we're going to do box on ramp. Let me draw. My weight is a little bit hot here. All right, I'm making the wedge part of the ground, and we have a box on it. Box on ramp. Yep, friction comes into it now, because if the ramp were frictionless, that box would definitely slide. So just a little cliffhanger there, and also, after, I guess on Wednesday, we have not only box on ramp, but we'll have boxes attached to a road. Yeah, it's true, it's coming. You can put boxes on roads. We are gonna put boxes on roads.
Yeah, that's how it is.
Here.
Lots of-
On the board. And don't worry, for those of you who are thinking, where's the math? It's coming.
Awesome.